Hey guys, welcome back to this class, Deep Learning Prerequisites, Logistic Regression in Python. In this lecture, we are going to look at a special case of logistic regression, one where we can find a closed-form solution to the problem. In general, we cannot, and will have to use gradient descent, but the solution here could be useful if your data is distributed in a specific way. The problem is this. Your data is from two classes, and they are both Gaussian distributed. They have the same covariance but different means, as you can see from this picture. For this example, you'll want to be familiar with the multivariate Gaussian distribution. So let's review Bayes' rule. This just says that the posterior, or P of y given x, is equal to the likelihood, which is P of x given y, times the prior, or P of y, divided by P of x. The likelihood part is the Gaussian we just talked about. We would calculate this by taking the data from each class and getting their means and covariances. The prior can just be the maximum likelihood estimate. So for example, P of y equals 1 would be the number of times class 1 appears, divided by the total number of samples. The next thing we could do is take Bayes' rule for the positive class, and expand the bottom portion so it looks like the top portion. Next, we divide the top and bottom by what's on top. Now you can see this looks kind of like the logistic regression sigmoid. If we put them side by side, it's easier to see. We see that the negative of the weight times x is equal to the log of the ratio of probabilities from the previous slide. The next step is to let P of y equals 1 equal 1 minus alpha and P of y equals 0 equal alpha, so our equations can look a little simpler. Next, we can expand everything inside the log because it's all multiplication and division, which gives us this equation. We can plug in the Gaussian PDF and we immediately see the benefit of taking the log since everything inside the exponential will drop down. We can also see that everything inside the square root will cancel out because it's just being subtracted from itself. Once we have the exponential terms logged out, we can expand them like this, so we just have a simple sum of products. Notice that the quadratic terms cancel out. That's where you see the x twice. Now you might think that if you see x transpose sigma inverse mu, it's not the same as mu transpose sigma inverse x. And it's good to be careful with things like this. But I would highly recommend trying it yourself on paper to prove to yourself that they are equal. Remember that the covariance and its inverse are symmetric. Once we've multiplied through the 1/2 and collected all the terms that depend on x and don't depend on x, we arrive at this equation. If you squint your eyes a little bit, you'll be able to see that this looks exactly like our linear classifier form, which is w times x plus b. Notice I've included the bias term explicitly here, since it's also explicit in the above form. Once again, we have one term that depends on x, this corresponds to w, and one term that does not depend on x, this corresponds to b. If you split out the terms for w and b, you arrive at these equations. I'll give you a second to look at them. You can always pause the video if you find it confusing or if you need more time. In our coding examples, we are going to use two Gaussians. One centered at -2, -2, and one centered at +2, +2. The variance of each dimension will be 1, and each dimension will be independent. So any off-diagonals in the covariance would be 0. As an exercise, I want you guys to prove to yourselves that the solution is w equals 4, 4, and b equals 0. We're assuming that we have an equal number of samples of both classes. So that means alpha equals 0.5. You also want to make sure that you can do the derivation in this lecture on your own, without watching the lecture. A couple quick extra notes. This method is also called linear discriminant analysis, or LDA. If the covariance is a diagonal matrix, as we've seen in the numerical example above, this is also an instance of naive Bayes. You should be able to figure out why this is. If we have different covariances, note that the quadratic terms would no longer cancel out. As an exercise, you might want to try deriving this quadratic solution yourself also. This is called quadratic discriminant analysis, or QDA. Also try writing your own code for QDA and comparing its performance against LDA. Finally, we should note that this solution is optimal, provided that the assumptions we made about the distributions are true. Generally speaking, they're not, so we would want to use gradient descent, which is more generally applicable.